In this video, we are going to study Laplace transform. Let ft be a given function defined for all positive values or zero value of t. Then Laplace transform of ft denoted by LFT is given by a definite integral from 0 to infinity of e raised to minus st into ft dt, which is a product of two functions e raised to minus st and ft, and can be evaluated by method of integration by parts, and after evaluation its value will be another function of s, capital Fs. For capital Fs to be a convergent value or a finite value, this s should be necessarily positive, because for negative values of s, e raised to minus st will be e raised to st, and as t tends to infinity, e raised to st will tend to infinity, and Laplace transform LFT will be divergent or infinite. Laplace transform has diverse applications, and we will study these applications in due course of time. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. We will start with finding Laplace transforms of some simple functions ft. Let ft equals 1 so that Laplace transform of ft, that is Laplace transform of 1, will be integral from 0 to infinity of e raised to minus st into 1 dt, which will be e raised to minus st upon minus s from 0 to infinity, which is minus 1 upon s into e raised to minus infinity minus e raised to 0. That will be minus 1 upon s into 0 minus 1. So Laplace transform of 1 will be 1 upon s. Next, let ft equals some constant k. So Laplace transform of k will be integral from 0 to infinity of e raised to minus st into k dt. That will be k times e raised to minus st upon minus s from 0 to infinity. That will be minus k upon s e raised to minus infinity minus e raised to 0, which is minus k upon s 0 minus 1, which finally will be k upon s. So this is Laplace transform of constant k. ft is e raised to at. So Laplace transform of e raised to at will be integral from 0 to infinity of e raised to minus st into e raised to at dt, which is integral from 0 to infinity of e raised to minus s minus a into t dt. That will be e raised to minus s minus a into t upon minus s minus a from 0 to infinity. That will be 1 upon minus s minus a into e raised to minus s minus a into t from 0 to infinity. That will be 1 upon minus s minus a into 0 minus e raised to 0, which is minus 1 upon s minus a into minus 1. That gives Laplace transform of e raised to at to be 1 upon s minus a, where s minus a is positive, giving s to be greater than a. Suppose if ft is e raised to minus at, then by changing sign of a, we will get Laplace transform of e raised to minus at to be 1 upon s minus of minus a, that will be 1 upon s plus a. Consider ft equals t raised to n. Before we proceed with finding Laplace transform of t raised to n, let us recall gamma function denoted by sin gamma. We have gamma n plus 1 equals integral from 0 to infinity of e raised to minus x into x raised to n dx. Now let us get back to finding Laplace transform of t raised to n. So Laplace transform of t raised to n will be integral from 0 to infinity e raised to minus st into t raised to n dt. We have to solve this integration by method of substitution, for which we will assume this st to be u. So t will be 1 upon s u and its derivative dt equals 1 upon s du. This substitution does not change the limits of integration, because when t equals 0, u is 0, and when t is infinity, u is also infinity. Therefore, this integral 1 changes to integral from 0 to infinity e raised to minus u into 1 upon s raised to n into u raised to n, and for dt 1 upon s du, which is 1 upon s raised to n plus 1 integral from 0 to infinity e raised to minus u into u raised to n du, which is 1 upon s raised to n plus 1. We compare this definite integral with this definite integral, which gives us gamma n plus 1. So we get Laplace transform of t raised to n equals gamma n plus 1 upon s raised to n plus 1. This becomes n factorial upon s raised to n plus 1 if n is a positive integer. So Laplace transform of t raised to n is gamma n plus 1 upon s raised to n plus 1. And when n is a positive integer, the same Laplace transform becomes n factorial upon s raised to n plus 1. Accordingly, Laplace transform of 1 will be Laplace transform of t raised to 0, which will be 0 factorial upon s raised to 0 plus 1, 1 upon s. So Laplace transform of 1 is 1 upon s. Laplace transform of t raised to 1 will be 1 factorial upon s raised to 1 plus 1, which is 1 upon s square. Laplace transform of t square 2 factorial upon s raised to 2 plus 1, 2 upon s cube. Laplace transform of t cube 3 factorial upon s raised to 3 plus 1, 6 upon s raised to 4, so on and so forth. In all these cases, n is a positive integer. Let us recall that gamma half is square root of pi. By using this result, we will find Laplace transform of t raised to minus half, where minus half is not a positive integer but a negative rational number. So according to this first formula, this will be gamma minus half plus 1 upon s raised to minus half plus 1. This will be gamma half upon s raised to half, but gamma half is square root of pi upon square root of s. So Laplace transform of t raised to minus half is square root of pi upon s. Let us find one more Laplace transform. Laplace transform of 1 upon square root of pi t. This will be 1 upon square root of pi being a constant into Laplace transform of 1 upon square root of t, which is into Laplace transform of t raised to minus half, which will be into root pi upon root s, cancelling root pi, we get 1 upon root s. So Laplace transform of 1 upon root pi t is 1 upon root s, and Laplace transform of t raised to half will be gamma half plus 1 upon s raised to half plus 1, which is gamma 3 upon 2 upon s raised to 3 upon 2, which is, by rules of gamma function, 3 upon 2 minus 1 gamma 3 upon 2 minus 1 upon s raised to 3 upon 2, which is half gamma half upon s raised to 3 upon 2, which will be, for gamma half we write square root of pi upon 2 s raised to 3 upon 2. At this stage, it is important to understand about exponential order. We have defined Laplace transform of ft as definite integral from 0 to infinity of e raised to minus st into ft dt. Same can be written as integral from 0 to infinity of ft upon e raised to st dt. Here, Laplace transform of ft exists if the right hand side of above definite integral converges or it has a finite value. For this, it is sufficient that the function ft is of exponential order. Ft is said to be of exponential order if limit ft upon e raised to st as t tends to infinity is 0, which is possible as t tends to infinity. Ft does not grow faster than e raised to st, or in other words, e raised to st reaches infinity before ft could. For example, limit t square upon e raised to 3t as t tends to infinity will be finite for higher values of t. Therefore, ft equals t square is of exponential order, say s equals 3. But on the contrary, limit e raised to t square upon e raised to 3t as t tends to infinity, which will be e raised to t square minus 3t, will be not finite, for the simple reason that for higher values of t, t square will be greater than 3t. Hence, the limit will be not finite. Therefore, ft equals e raised to t square is not of exponential order. Ft being of exponential order is just a sufficient condition for Laplace transform of ft to exist and not necessary condition. For example, we have already seen that Laplace transform of t raised to minus half is root pi upon s, which exists even though t raised to minus half is not continuous for t to be negative or equal to 0, because t raised to minus half, which is 1 upon root t, tends to infinity as t tends to 0. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. See you in the next video. Until then, keep watching Number Collage. Thank you.